Thanks very much. I thank the organizers for the invitation, and I know that I'm the only thing standing between Paul and his first beer of the day, so we'll try to keep this as brief as possible. Yeah, so it's an absurdly long title. The last time I gave this talk, I only got I got the third one, but not the first and second subject, so I'm hoping to do more in this talk. That sort of doesn't seem to go with the previous comment, but we'll see how it goes. This is, so maybe I'll join all of the other speakers in trying to say how this has anything to do with the themes of the conference. So there are going to be invariants, but they're definitely not higher. There's going to be algebraic geometry, which is not going to be derived. Poincare duality is going to be used, but I'm pretty sure that's not what you guys had in mind. There will be a relationship to Picard groups, which I'll make a comment about later. But I think still thematically there is something here in that the point of this talk is very much to try to answer algebra-geometric questions using topology and in particular sort of structured, operatic structured gadgets. All right. So let me start with some algebra. So my goal is to get towards something called Mahle's conjecture, originally stated by Gunther Mahle for number fields. But let's start with a simpler thing, the inverse Galois problem, which is probably familiar. So it just asks if G is a finite group, does there exist a Galois, or does there exist an extension K over the rationals such that G is isomorphic to the Galois group of K over Q? And if K is not Galois, I mean the Galois group of the Galois closure of K. Right, so this is obviously a very well-known and very famous conjecture. It is certainly not known. It's known, for instance, if G is solvable. This is apparently work of Shafarevich. And my understanding is that generally this is the sort of thing that there's various cases in which it's known to be true, but there's sort of no consistent story besides the solvable case. Okay, so Mahle's conjecture is taking this thing that we don't know the answer to and making it far, far worse. So to state it, I need to set up a little bit of language. So let's do that. So if the degree of this extension is n, then the Galois group of K over Q is going to embed into the symmetric group on n letters. Really, it's the symmetric group on the n different embeddings of K into its Galois closure, right? It acts transitively on those because that's what Galois groups do. So this is not just a subgroup, it's a transitive subgroup. So we can extract a few pieces of data from this. So if little g is an element of Sn, and I'm probably thinking of an element in the Galois group, I'm going to define the index of G to be the number n minus the number of orbits that under G. So the cardinality of the set 1 through n modulo the subgroup generated by that single element. So for instance, if G is a transposition, I mean, its orbit is just the two elements that it transposes. Or the only thing that moves around are those two elements. So when I quotient by that, I've just taken two things and turned them into one thing, and the remaining n minus one things are the remaining n minus 2 things are the same, so then the index is 1. But if G is an n cycle, then the index of G is n minus 1, because it only has one orbit. Okay, so that's some number that you can extract from elements of the symmetric group. If I have a subset C inside of Sn, little c, then we're going to define, and actually maybe I'll just do this. If C is sitting inside of a group G, which is sitting inside of Sn, and G is really supposed to be this Galois group, then we're going to define A of G comma C to be, well, what do? I minimize the indices of G when G lies in that set. Right, that's some number between 1 and n minus 1, and then I invert that. Okay. I suppose the identity has index 0, so I don't want to do that. So I'm only ever going to consider elements G that are not the identity. So as a result, this is the smallest possible index. This is the largest possible index. So it's certainly the case that 1 over n minus 1 lies between A of GC and 1. So just bear that in mind. This number A of GC is some constant that's bigger than 0 and smaller than 1. All right, here we go. All right, so that's the index. Let's see, what else can I throw at you? There's also the discriminant of the number field, and I won't write down the definition, but I'll say it to you in words. Pick a basis for the ring of integers of your number field. You map them into the complex numbers using all of the different embeddings of the field into the complex numbers. It's going to give you, there's n embeddings and there's n basis elements. It's an n by n matrix of complex numbers. You take its determinant and square it, and that's the discriminant. That's a totally enlightening piece of information. So the discriminant, a much more useful piece of information, the discriminant delta k has a prime p dividing it if and only if the prime p ramifies in OK, in the ring of integers of the number field. All right? Any questions? OK is the ring of integers in the field K, in the field extension K. All right. OK, so with that, with these pieces of data, I can make a definition for you. So let's let so fix G, a transitive subgroup of Sn, and then I'm going to define a function for you. So let's let n sub G of x is a number. This is going to be a function. N sub G of x is going to be the following thing. I'm going to take all extensions k over q, which are degree n, and their Galois group of k over q is isomorphic to G. So let's pause for a moment and acknowledge that the inverse Galois problem is asking, is this set empty or not? So far, this, yeah, all right. That said, I don't know, even though I don't know whether it's empty or not, I also don't know if it's non-empty, whether it's finite or not. So what I can do to make it finite is insist that the discriminant be less than x. So it's a theorem of Hermite from a very long time ago, that this does indeed, the set of possible k that satisfy this is finite, so I'm going to just count them. All right? So that's a number, and it's a number which depends upon my choice of x. So this is a function of x, and it's by force a non-decreasing function of x. And the inverse Galois problem asks, is it ever positive? So here's a completely ridiculously bold conjecture in light of that fact, that Mala made in, I think, 2002, which is that there exist constants C1 and C2, which are greater than 0, such that for all epsilon greater than 0, C1 x to the a of g, comma g minus the identity is less than or equal to n sub g of x, which is in turn less than or equal to C2 x to the a of g, g minus 1 plus epsilon. Sorry, that's epsilon. All right. So I'll forgive you if you haven't spent enough time around analytic number theorists to parse this. This is saying that this number of extensions grows polynomially, where the degree of the polynomial is this number between, well, polynomial possibly with a fractional exponent, and or rather it grows at least polynomially, and at most a little bit more than polynomially, and a little bit more that really that plus epsilon is code for I'm not allowed to multiply by any higher powers of x, but I am allowed to multiply by powers of log of x. And that would be kosher. Right, so this is an enormous strengthening of the inverse Galois problem. It's known if G is abelian. That's due to Wright, and you might imagine this comes from class field theory. And in fact, this is very ahistorical. Wright proved this before Mullen made the conjecture, and this fact was sort of part of his motivation for coming up with this conjecture. It's known when G is S3. That's work of Davenport and Heilbronn, again, before Mullen's conjecture. And it now, as of a couple of years ago, follows from Bar-Gava's work that it also is true for S4 and S5. And I think this is literally all of the groups for which we know it's true. So that said, there's plenty of numerical evidence that suggests it's true. Yeah. I'm sorry about the clunkiness of this exponent. There are variants of this where instead of just saying arbitrary Galois extensions, you specify something about monodromy of these extensions. And if you restrict the monodromy to be in your subset C, then you should change your conjecture to fit the story. And that's actually what we'll do in a minute or two. Let's see. What else can I tell you? There's a version of this, or there's a variant of this conjecture where instead of asking about the growth of Galois groups, you're asking about the growth of Picard groups, of class groups of number fields. And that's a conjecture due to Henri Cohen and Hendrik Lenstra. And indeed, that is, we've certainly heard a lot about Picard groups in the last couple of days. I don't feel like this is the sort of thing that, well, I don't know. It's a nod at the least to the subject of the conference. All right. Right. So let's take this conjecture and worry about it later. And because we don't, because it looks pretty hard, let's not try to prove it. Let's instead change it. Let's change it around and try to make it easier. In fact, because it implies the inverse Galois problem, let's just even start with the inverse Galois problem and change it and make it easier. So the inverse Galois problem was asking if you've got your favorite finite group, does it exist as the Galois group of an extension of Q? But why Q? Why did we start our lives with Q? So let's go back to the inverse Galois problem and ask, let's change Q to another field. And the sort of fields that I want to consider are, yeah, and I'm going to apologize for this. This is going to be a lowercase k of t. So the ring of rational functions over k. Over some little field k. And there's something wonderful that happens here that gives us a toehold on the problem that we certainly did not have in the rational case. And that's the fact that the problem starts to become much more geometric. So what do I mean by that? So if I have an extension k over little k of t, this is going to correspond to an algebraic curve sigma defined over the field k and the map pi from sigma to the affine line over k. And how do I do this? Well, sitting inside of big K is the ring of integers, OK. And sitting inside of little k of t is its ring of integers. And that's the ring of polynomial functions on k of t, right? And if I just apply spec to this inclusion, I can take sigma to be spec of OK. And I know that spec of k adjoint t is the affine line. And that gives me a map to the affine line over k, the dual of that inclusion. All right. And what else can I say about this? It's not just any map. There's the fact that this was a field makes this a geometrically connected curve. What else do I know about it? And if I've got a map between two one-dimensional varieties, this is going to be a sort of a ramified covering. So pi is a ramified covering. So what does this do for us? On the one hand, back here, we just had field extensions of the rationals, and we're sort of staring into the abyss, because there they are, and what do you do with them? But here, field extensions of k adjoint t, well, we've got some sort of geometric phenomenon going on. They're algebraic curves that map to the affine line. All right. So let me prove to you that the inverse Galois problem holds in this setting for when little k is c. So when I'm looking at rational functions with complex coefficients, the inverse Galois problem holds. So what do? I take my finite group G. Since I know that it's finite, it in particular is surjected onto by a free group of some rank, some finite number of generators. And I'm a topologist, so I know what group that is. That's the fundamental group of C minus an n-tuple of points, right? Or bouquet of n circles. But again, because I'm a topologist, I know what homomorphisms from fundamental groups to groups surjective homomorphisms look like. They're the same thing as covering spaces. So from this, I can produce the following picture. I'm going to take C minus these n tuple of points, and I'm going to construct some covering space, which I'll call sigma prime. So this is going to be an unramified cover, an actual covering space. And by construction, the Galois group is G. It's an unramified G cover. And that's not what we want, right? We want a ramified cover not over some punctured plane, but all of the plane. But now you sort of see the answer. There's kind of one way to fill this into being an actual ramified cover. So I sit this guy inside of C, and I claim that there exists a essentially unique sigma and pi that closes it up. So this is this is now a ramified cover, and it's ramified at this set, Z1 through Z. How do I do it? How do I close it up? Let's sort of draw the complex plane. Let's take a bunch of points in the complex plane. Let's say that's these points. And around each of them, I just grab a little circle. I lift that circle, I lift that path, say starting here, up to a path in the covering space if this is the curve gamma, that defines an element which is the monodromy of gamma in the group. And that monodromy, let's just call it G, little g.